this derivative would simply be 0. It would be only this one, del sigma plus x mu L. This is a function of this. So we have our definitions here, x mu L. Okay, I have written both of them together. Anyway, we have x mu L here and x mu R here, and we have to so we have to take derivative only for this. This is x mu of sigma plus. Okay, this is x mu of sigma plus. Okay, so we take derivative of this with respect to del sigma plus, and this is equals to, I can maybe write the result here, 0 plus ls square by 2 p mu L plus iota ls by root 2 k not equals to 0, 1 by k minus iota k alpha mu k e to the power minus ik into sigma plus. Okay, this is sigma plus. Okay, so we take this, and this is all. The other term, derivative of this simply vanishes. So it is this part, and this is equals to ls square by, let me just write ls square by root 2 into ls square by root 2 into p mu L for a different region, plus this minus iota plus iota goes away, gives me, and this k cancels with this k. So I have ls by root 2 summation over k not equals to 0, and then I have alpha mu k e to the power minus ik sigma plus. Okay, now I written it like this. Is I want to, here I have a summation over k for all k except at k equals to 0, but I can absorb this term into this term because I no longer have k in the denominator. Therefore I could absorb this term into this, and this is alpha mu 0 equals to ls by root 2 into p mu. Okay, p mu of p mu L, or p mu L is all right, no problem. So this we could absorb in this, and therefore we could write it as ls by root 2 into n going to minus infinity to plus infinity, and including n equals to 0, alpha mu n. Here term is also okay. This term is also included, and once we can write it in this form, it becomes rather straightforward to write down t plus plus. So this is going to be a square of del plus x mu whole square, and now this can give me a square of this ls square by 2 summation. I can put 1 or 2 over, let me say, m L and m from minus infinity to plus infinity, minus infinity to plus infinity, and alpha L alpha M, a scalar product of two alphas in the d-dimensional space. A scalar product of two alphas, which means if you like, you can say alpha mu M dot alpha like this into e to the power minus Jutta times M plus L sigma plus. And this is what you can usually write it as alpha, what have I done? Alpha mu, oh, this is L, alpha mu L. So I can write alpha L dot alpha M. So it's a scalar product of these two. One mu is upstairs here, one mu is downstairs here. So it's a scalar product of these two mu vectors. Right? Mu once is upstairs, one it is downstairs. So this is, for short, I would write it like this, or one has to write it like this. Okay? Like A mu. Alright? And times this. So that means I could put M plus L equal to something different. M plus L, let me put equal to N, then L would be M minus N. And therefore, I could write this solution in a much simpler looking manner. So let me remove this. So what you have is this equals to Ls square Lm equal to minus infinity to plus infinity 1/2 alpha L dot alpha M times e to the power minus I M plus L sigma plus. And now putting M plus L equal to N, or N equal to N minus M, I could write this expression as Ls square M equal to minus infinity to plus infinity 1/2 of alpha N minus M dot alpha and times e to the power minus In sigma plus. And for this I can use a new notation, and I could call it Ln. I could define it by Ln. Then I could call this as Ls square M equal to minus infinity to plus infinity Ln e to the power minus In sigma plus, where Ln is defined by this and M is summed over from minus infinity to plus infinity. These would be called as, because this object has to vanish, therefore this object has to vanish, therefore this object has to vanish. So therefore Ln would be 0. This would give rise to me an infinite number of constraints on the theory. These are called as Virasoro constraints. And let me just mention the result for the other. We can continue it within in the next week. A similar condition would be just the other condition. I could calculate del minus x mu in the same manner, and then this would be Ls by root 2 into Ls by root 2 into P mu, which I would substitute for beta mu 0 plus Ls by root 2 into k not equal to 0 beta mu k e to the power minus ik sigma minus, and then I could absorb this into that. So I would write Ls by root 2 summation over n minus infinity to plus infinity beta mu n e to the power minus I n sigma minus, and so here we have included beta 0 mu also in this series. Okay, and then we could obtain 0 equal to t minus minus, which would be del minus x mu whole square. Then this becomes much easier. Let me just write down Ls square times sigma equal to n. Now I have a different notation, L n bar e to the power minus I n sigma minus. Here my Ln bar equal to 1/2 of summation over m, and what was this